I could use some refreshing on number 8 on our
Number which?
number 8 on our turn in. I think it's no, but I wanted to talk through.
Right, for the saving for retirement or mortgages, which topic?
Oh, I'm sorry, mortgages.
Mortgages, okay. Sure, we can do that. Okay, so we're having two situations. One is the top one with the gray background. We worked through that example problem together and got all those numbers. Now we're saying, what if there's another family that does everything the same, except they're taking the 30-year and making it a 15-year? So if your loan is only half as long, does that mean that you would get half the size house and half the down payment and half the monthly payment and things like that? And you're nodding your head no, and that is correct. It doesn't work that way. So if we go to the mortgages part, so 6% in 30 years is $6. 6% in 15 years was $8.44. So if those numbers were, one was half or double of the other, then maybe that would work. Maybe something would be half or double. If it costs twice as much, maybe you get half as much house. But it doesn't work that way. So I don't even have to do any more math. I can just say that no, other numbers don't. Have a times 2 or divided by 2. Actually, while my webcam is there, what if I move the pictures of you closer so I'm not looking off to the side quite so much? Okay, other questions on homework? Anything in the saving for retirement section that you want us to do? Should we try number 3? Should we do a different duck for number 4?
3 would work.
3 works?
Or 4.
So by the way, if you haven't followed this link, I recommend it. Payday loans have a bad reputation, but they actually are very useful businesses in many communities, and on your own time, you can read about why. Okay, so Oregon had a Senate bill many years ago that said payday loans could only have 36% interest or less. And that was important because before that, the businesses sometimes were quite predatory and could have interest rates as high as 120%. Nationally, when there's even less limits, there are some payday loans as high as 7,000%, which would be astounding. So yeah, that's where the bad reputation comes from. So let's pretend that we're back in the days with 120%, and we have what is the kind of national average payday loan situation. Someone needs a loan for 2 weeks, and they're paying 120%. So we had our simple interest formula. And I recommend that we write everything out on the side and not jump to plugging things in right away, especially with a word problem like this that has a lot of red herrings. There's numbers like the 7,000 that are just not part of the problem at all. So let's list out. We have simple interest, principal, rate, and years. Okay, so in this case, the interest was $16.15. The principal, we don't know that. That's the how much was borrowed. That's not right. The rate is 120. Since I'm putting it in a calculator, then I'll want to get out of percent format and into decimal format. And that's per year. And per year is good. This is a simple interest, so we always want everything in years. If something's not in years, we need to fix that. And speaking of that, the time frame we have is 2 weeks, so I have to fix that. How do I make that some amount of year?
250 seconds.
Yeah, 2 over 52. 2. So now I'm ready to start. I've figured out what I have, what I need to solve for. Everything that has a time associated with it is years. Okay, the rest is easy. The calculator does its work. So $16.15 is my principal times 1.2 times 2 divided by 52. And I'm doing a little switch here. I am changing the fraction bar into division. Everyone okay with that? I could write it as another line, but to a certain extent, I don't want to write extra lines just because I'm lecturing. Okay, so that 1.2 looks funny. I have a bunch of stuff. I'm not sure what 1.2 times 2 divided by 52 is, but whatever it is, it's one number. So just like we did last time, I'm going to capture all of this because people will have different personal styles. And what some people will do is say, I want to write a little bit more. That makes me happy. So I am going to find out that this stuff to the right-hand side of P is one number. So what is that? 1.2 times 2 divided by 52. Now I have number equals P times number, and I know what to do. I divide by that thing, right? P times something, the opposite is P divided by something. I don't want to round in the middle, but that's okay because my calculator has a previous answer key. If not, I just try and type out this without rounding as much as I can. But since my calculator does have a previous answer key, I can just have $16.15 divided by previous answer, and there we go. So $349.92. Everyone okay with that?
Yes.
Other people will say, I understand this, but I don't like this step. That's just extra work. So they will say that whatever this is, I can divide by it all at once, as long as I have parentheses to make sure that it's really all one thing. So they will put in the calculator $16.15 divided by parentheses, blah, 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 close parentheses, and they will get the same answer, the 349.92, a little quicker. They get to skip a line. So it's up to you. Sometimes this slide makes people uneasy. They want something that has a number is our letter times one other number. So we can divide both sides by whatever is stuck onto the letter. And that game they are quite used to, and making it look like three things just seems funny. If that's you, that's fine. You don't have to do that. You can do it this way and make it one number first and then divide. Okay, last time we met, we did number 4, but for the annual one, let's do number 4, but for one of the different ones. So what interests you? Should we do the weekly case or the monthly case. We've done the annual case.
Let's do weekly.
Weekly, okay. So we need a different formula. We're not in simplest interest anymore. We're in compound interest. And this one I'm going to also do in two different ways. So I will put that on another slide. Okay. Some people like the compound interest formula in its generic form. Just like we have to fidget with things to make the time match, we will have to fidget with this to make everything weekly, because it's weekly compound interest. Other people say, I don't want a generic formula. I want a formula that's specific to weekly. I don't mind writing down more things because it's open notes anyway. So they will use a different version of the formula that reminds them that for weeks, the fidget is 52. So we'll do this both ways so both people are happy. You, of course, only need to know one way of doing it, but I don't think it will confuse people to see the other way, and it might even help. So, as always, our good habit when we're plugging things in the formula is to get organized first before we dive in and plug things in. Okay. So the final amount is what we're solving for. How much money will they have after 13 years? It's 9%. And the principal is 5,000. Okay, what do I have to do to get ready?
Write in all the, oh, never mind. Times the principal by the 1 plus interest rate per payment.
I'm not ready to plug things in yet because I don't actually know how many payouts I have or what the rate per payout is, because these are both right now in years.
We got to change the years to weeks.
Yeah, we need to make it weeks. So let me put it in bright red to remind us we need to change.
Anything.
So to change a year, we have to take this 9% and share it among 52 different weeks. So we're doing divided by, like we're dealing out cards. And how many payouts do we have? Well, each year we have 52 weeks. So we have 52 times 1, and then 52 times 2, and then 50, all the way up to 13 years.
So 9 divided by 52. is 1.7.
Yeah, we get 0.0017, blah, blah, blah. And for 13 times 52, we get 676 weeks. Okay. I'm going to do this now 2 different ways because some people hate long decimals and other people's don't. So the straightforward way is to just plug things in. Everyone happy with how I took the 1 and put a 1 in front of my decimal? Okay, so my calculator does the work. What is that? I'll take that thing, exponent 676 times 5,000. Oh, something went funny. Okay, we get $16,093.68. Everyone get the same? Your exponent key works the same way mine does. Other people will say, this long decimal looks too ugly. I don't want that on my paper. So what they will write is the same kind of thing, but they're going to take the 0.09 divided by 52 and just plug in that. And because it's not one number anymore, they have to put the parentheses back around. Otherwise, the exponent is only going to do this part and not the +1, and they'll get the wrong answer. So there's 2 different styles. Some people say long numbers are great, I don't care, my calculator does it. Other people say parentheses are okay, I don't care, my calculator does it. Either way works. Then after you look at this, the third style is to say the divided by 52 and times 52 that we did in red. I don't want to have to think about the general case. So I'm just going to pick the specific formula for weekly. It has the 52 built into it, and then I can plug things in more directly. And they will also get that same answer, whatever it is. 16,093.68. Notice that if you're doing this, you need parentheses twice. Once is because you are not smushing this into one number off on the side. And a second time because you're not smushing that into just one number off on the side. You don't want your calculator to make the 13 the exponent and then take just some number and multiply it by 52. You need this to be part of that 676 in the exponent.
I guess I'm just not understanding how to punch this into my calculator because my calculator keeps saying overload.
Okay, well, let me stop the screen share and go to highlight your video. And if you want, you can just turn on your video and we can look at your calculator.
Oh.
Okay, spotlight video. I can't see it clearly enough with the webcam. So you have parenthesis keys.
Mm-hmm.
My first guess, let me show you my webcam, is that when you have a calculator, there's always a secret reset button on the back that you push with a pen or a paper clip or something. And so at the top, if it doesn't say degrees, if it says something else in the screen, then
It says degree, but up in the top right-hand corner is an arrow pointing up.
I don't know. We'll try your secret reset button. And if that doesn't work, then
I gotta find something.
we'll try again.
Well.
And you can test it on a simpler thing like this. So if you try a simple problem without an exponent, see if the parentheses work so that you get 48 instead of 24.
$48. Yep.
So that one worked?
Mm-hmm.
Okay, so now we'll go back to the real one. What I'm going to actually put in my calculator is 5,000 times parenthesis key 1 plus 0 point, I guess I don't even need the 0. I'm just putting it in the calculator. 0.09 divided by 52, close parentheses. Your calculator might have a key that looks like a caret symbol, or it might have a key that looks like y to the x.
Yeah, mine says EX.
EX is the wrong thing. There's another key to find somewhere.
Well, let's see here then.
So that was your problem.
There's a key that says X2.
There should
It's
be
right
one
above
either
that
the caret
one
symbol
still.
or
Oh, okay, I see it. Okay, yeah, I got that. All right.
good. Okay, that's good because you can't do your homework without it. So I am glad we took a moment and found it.
And then parentheses 13 times 52 close parentheses equals. Well, I'll be damned.
Yes, there is a key on most calculators that looks like EXP, and that's for scientific notation. It is not for exponents, even though it looks like exponents. Never use that key. Not our class.
Good to know.
Okay, yeah, well, that's
Thank
why we're
you
here.
very much.
Okay. So that was a good review. We did a simple interest problem. And for simple interest, there's only really one formula. You just have to fidget with the times to make sure everything is years. For compound interest, they usually give you things in years, and you have to fidget to make them whatever the compounding it says, in this case, compounded weekly. And you can either do that with a general formula and remembering to fidget on the side, or you could be someone that likes the specific formulas because, hey, dump loads of parentheses, not a problem, I have a calculator.
Oops.
Okay, let's keep going. The annual effective interest is something that you probably don't need to know about, but there's at least one degree or program or major that's asking you to teach this, so we do. And this is an interesting thing where, oops, that one. We say, what if we were to invest only $1? So I'm going to go back and grab all of this stuff so I don't have to write it again. Okay, so what I'm solving for is the final amount. And our principal is only $1. We'll talk about why in a moment. The rate per payout is whatever we're using. So what should we do that's like a good rate we care about? 22% for credit cards? Sure, I see a nod. And let's say this is monthly, so we'll divide by 12 months. And the number of payouts, we're going to start with 1 year. And since we're doing monthly, we need a times 12. And then we plug everything in.
Oh, for Pete's sake.
So we have our interest, our principal, the $1. We're multiplying that with the 1 plus trick and the 0.0183 repeating, and the exponent is 12. And we get whatever that is. So 0.2. Then we think, well, that's how much is in the account at the end of the year. How much of it was actually interest? We start with $1. So we need to subtract away the green dollar. And the interest was 24 cents. So this is kind of funny. The rate was 22%. But what actually happened is we went up 24%, right? 24 out of the 100 cents we started with. So where did the extra 2% come from?
Isn't that just supposed to be like the unspoken like rule of what you have to pay every month, the extra 2%?
Yeah. So for example, if we were looking at lecture last class, oh, not that one. This one, 2 classes ago.
That's the one you just clicked on, I think.
That's the one I just clicked on. Is my link broken? Or did I just click badly? Okay, remember the 6 years of rent? How a 5% of 30, I'm sorry, a 5% of 500 is 25. And if we had 6 25s, that would be 300. But it was actually more than that. It wasn't a 30% increase, it was a 34. These got bigger and bigger, and that's where the extra 4% came from. Does that ring a bell? If not, don't worry about it. Yeah. So the same thing is happening. The interest builds on itself. And so whatever we had to owe in January, we also have to owe in February and get interest on it. And whatever we owe in February, we'll also owe in March and have interest on it. We're not making any minimum payments on this credit card. So that's why we get this extra 2% by the end of the year. So somebody wanted a name for this. So they call it the annual effective interest rate formula. And all they're saying is take the compound interest formula. There's no principal here because we're using a principal of $1 and times 1 doesn't do anything. And at the end, we're subtracting that $1 to get just the interest amount. And then we can see that it's labeled 22% interest per year, but it actually feels in your wallet like 24% because of the way the interest builds on itself. Make sense?
Yeah.
So not terribly important, but if you want it, then there you go. That's the annual effective interest rate. Okay, now this part is important for everybody. This is the rule of 72. Sometimes we just want a quick and easy estimate of compound interest. So imagine that we invest $1,000 and we get 10% every year and it's compounded annually. How long would it take? And I'm not going to take class time to do this, but you can fill out problem after problem. If the exponent is 1 year, if the exponent is 2 years, if the exponent is 3 years, and so on, how long does it take to double? It will pass the 2000 mark between 7 and 8 years. The 8th year is the first year it's over 2000. Everyone happy with that? We could do that if we wanted to take all the time. What if instead of 10%, a 0.1 here, it only earned 7%? Then it would be slower. Now we have 0.07s in all of these spots. So the exponent that finally gets us past the $2,000 cutoff is 11 years. So there is a pattern. If the rate was 10, it would take 7 years. If the rate was 7, it would take 10 years. And why does that say 72? That's wrong. I should fix that. Anyway, the point is that if you do this, it's always true that the numbers that multiply together are like 72. So let's make this nice and big. If I have a 3% rate, it's going to take me about 24 years to double my money. And 3 times 24 is 72. If I have a 6% rate, it's going to take me about 12 years to double my money. And 6 times 12 is 72. If I have a 12% rate, it's only going to take me 6 years to double my money.
72.
And we've seen that when the numbers don't actually make 72, then they're pretty close. So, or a 10% times 7 years, that was about when it doubled. Or a 7% at 10 years, that's about when it's going to double. So we can see if you're starting to save for retirement, we're finally really talking about that, then the compound interest formula tells us any account with 3% isn't going to matter. Doubling your money every 24 years, you're going to get old and die before you can retire off that. We need some percentage higher than that. If you could possibly get a 12% return, which is not terribly likely, then your money doubles every 6 years. So that would be really cool, and so on. So this lets you skip our formula. We don't have to do the compound interest formula. We can just estimate it and say about how long does it take something to double. So this column is the annual rate. And this column is the years. If you had a savings account that only gave you a 2% rate, how many years would it take to double? What do we multiply 2 by to get to 72?
Sorry, my thing was flickering in and out, trying to get it refreshed. I got a new computer coming. I just
36.
waiting for it.
36, yeah. So savings accounts are terrible for retiring. They're good if you need your money handy, but 36 years is way too long to be helpful. Okay, and that's the end of compound interest. The rule of 72 does work if you have your money, but that's not terribly practical. So. Okay, it's 11:09. We have 20 minutes. We are not going to finish this sum of annuity due formula, but we're going to start it, and then we'll talk about it more when I see you again. So far we have two formulas, simple interest and compound interest. Neither of them is really what I want. Nobody, when they save for retirement, puts a bunch of money in the bank and then ignores it for 40 years, right? Whether you get simple or compound interest, all of these involve one payment that you just watch get bigger and bigger and bigger. So we need a different formula that says I am going to repeatedly deposit my money. And in real life, that's still a terrible oversimplification. No one deposits the same amount every January. We all start out young with jobs that don't pay much. For me, it was flipping pizzas at Little Caesars. And then as our career progresses, our income goes up and we get more money. And so we save very little when we're young, and we save more and more later in life. And then there's things like, you know, kids and college and houses and things that make certain years unusual. But we're still building tools, and we'll see how we can use the tools, even though they're oversimplifications, to help us actually plan for retirement next week. So the next tool we need is, what if we were unrealistically predictable and every January saved the same amount for retirement and kept putting that money in? And the answer is you get this sum of annuity due formula. And it's too complicated, unfortunately, to have us actually find a pattern and discover it. We used that years of rents table to find the compound interest formula last class. So we discovered why that pattern works. This one, the pattern is just too complicated, but we can just use it. That's okay. It's like those metabolism formulas that we used even though we couldn't discover them ourselves. So how we use this is exactly the same as before, and it looks longer, but it's actually easier than compound interest. And as we do this first example problem, I'll show you why. One question you might have right away is, what's up with these square brackets? And they are just parentheses, but they are from a website with typing. So if I was writing this by hand, then I would take those parentheses and I would sort of make bigger parentheses there to show that they are outside these inside parentheses. My eye likes it when they're two different sizes. But I can't make big and small on a typewriter. So the tradition is, back from the days of typewriters, that you alternate. And if you have normal parentheses inside, then the ones that contain them, you use square brackets to help see. And here on the website, we're doing a little of both. These are slightly bigger, since websites can do that, as well as alternating from round parentheses to bracket parentheses. But all they are parentheses. It's just trying to make it clear when you're reading it for your eyeballs. Okay, but how we do this is just the same as before. We want to list out our things, and these look very familiar. We have what's the final amount, and because there's an exponent, that's always what we're going to solve for, just like compound interest. There's a principal, and this principal is called a principal, but it's a completely different thing. This is a repeated deposit. It shouldn't be called the same thing, but we don't get to change it. We are no longer only once depositing money and watching what happens. This is that every January we're putting in a certain amount of money. Oops, and I grabbed the wrong problem. I grabbed a compound interest problem that didn't do that. So let's actually get the right problem. is that right? Yeah, this says each year. I don't know why I'm misreading it. Okay, so they're saving each year for retirement. Okay, the rate per payout is 8%. And the number of payouts is 45. Okay, everyone okay with my plugging things in? Or not plugging things in, but writing things out. So we don't have to fidget. Unlike compound interest, there's none of this divided by 52 times 52 garbage. We never ever use the sum of annuity due formula with a monthly or a weekly or a semi-annually or any of that other baloney. It's always just for a year. So no fidgets. That's why this is an easier formula. It's longer, but the calculator does all that work. For us, it's simpler because we never have to do any of that, adjust things to be months or weeks or so on. Okay, so now we just plug things in. Oops, that's not a good line. So final amount is the principal times the 1 plus rate. Now the 1 plus rate looked a little complicated, but all I'm doing is putting a 1 in front of the rate, just like before. Times, now the bracket parentheses I do need. I can't leave those out. Well, I can't fit it in. Let me squeeze things a little more. Okay, so that doesn't look so bad. Notice that wherever there was a 1 plus rate, I just put a 1 in front. I don't actually need these curly parentheses. Be careful that you don't put a 1 the last time. There's no 1 plus at the end. It's a common mistake after you've just put the 1 twice to put it a third time, because you're on a roll. Okay, and now the calculator just gives me an answer. So 1,200 times 1.08 times open parentheses
500,911.
Okay, let me get that too. So 500,911.
Okay, 0.28, sorry.
So how much money did they put in? If I do 1,200 times 45, you get 54,000.
Wow.
So over their lifetime, they put in 54,000, which is a remarkable amount of saving. But they got to live off a lot more than that because of all the interest. As you mentioned before, this is a tool. We'll see how to use it to get more realism later, but it's probably true in real life. Someone would save a lot less money when they're young and more money when they're older, and it would work out similar. But for now, we're just pretending that it's always the same. Okay, we have time for one more. Should we do another?
Sure.
Okay, so let's say let's see, I'm actually going to move that to here. Okay, so here is our first actual advice on how to save for retirement in a math class that's been promising this. So lots of people have something that they spend money on regularly. Maybe it's Dutch Brothers, maybe it's smoking, maybe it's going out to eat, whatever. So let's see how much cutting back on such a thing can add up to over a long time. So if we have 570 per day, how do we find out how much he's spending per year?
Multiply that by 365.
Yeah. So
Holy cow. 20,805.
2,000.
Excuse me, I'm sorry. I missed the decimal point.
Okay,
2,080.
everyone happy with that? So now we're going to say, what happens if somebody puts that into the sum of annuity do formula? So the 2,080 and 50 cents. Now, last time we used this formula, I had all this stuff in blue on the side, but I don't need that. Because there's no fidgets, that's all just kind of a little overkill. So it's 6%, so I can just write a 1.06. $40 years. And not 1.06, just 0.06.
$341,301.20.
Okay. So I'm not sure if this is enough to retire on or not yet. We'll talk about that when I see you next class. But that's an awful lot of money just for smoking. And if it's not smoking, that's something you or someone you know does. It might be Dutch Brothers or going out to eat or something else like that. So changing a daily habit can pretty much get you most of the way to retirement.
Jeez.
That's crazy.
It is. Let's actually
I need to
talk
quit
about
smoking.
that. Since we have a moment, then the typical rule for savings, and this isn't my rule, this is just if you talk to investment advisors, so take it with a grain of salt, and things depend on if you live in Oregon or New York City, right? But the idea is to have, at age 65, saved $20 for each dollar that you will need to spend while you're retired. You'll have some income from Social Security and pensions and stuff, and you'll have expenses. So the income will cover some of the expenses. The uncovered expenses, for every dollar of that, you should have $20 saved. And that basically means for the 20 years from 65 to 84, you will use up your $20 as big as you need. And if you live longer than 84, that's great because you will have interest. Remember the annual effective interest thing. So during year one, the other 19 years, the other $19 per dollar will be earning interest so that it doesn't run out. So that's the game plan. A typical American retirement expenses are greater than their retirement income by about $20,000 a year. People have some income, but it's not quite enough to cover their retirement expenses, and usually they need about $20,000 a year extra beyond their retirement income. And again, if you're in New York City or Eugene, this is very different. So talk to people around you if you actually are doing this as a big idea. So if I take this number and multiply it by the 20, then the average American, the typical, the representative numbers, we're getting back to typicality, needs $400,000 saved for retirement. So you don't need to be a millionaire. And we just saw that you can get almost all of the way there sometimes just by adjusting your spending, even if you don't think you're wealthy. What we'll talk about next class are these three sisters. And if you want to go ahead and act smart in class and find the answers first, you can. But one of them, for 10 years, will put all their money in savings. And then once they turn 35, they'll stop savings, let it build with compound interest, and spend all their money on vacations. My kids have stopped barfing, let's go on vacation, right? Whatever. The second sister does the opposite. When she's young, she never saves at all. She just goes on vacation. But then once she hits 35, she starts saving for retirement and doesn't vacation anymore. Maybe she had kids later, or maybe whatever, right? And the third sister says, you two are extremists. I'm always going to go 50-50, spend half of it on savings and half of it on vacations. So we're going to find out what they have at age 65 and be surprised at what the answers really are. So that's our fun project to do together next time. The homework, when I look at the homework, is a little tricky for this topic. So let's look at the random problems first. Because what happens is, remember Sir Topham Hatt we did last time? You had a two-part problem, compound interest with one type of compounding and then compound interest with another type of compounding. And you used the end result from one as the principle to start the next. So we're doing something else similar here. Somebody is going to start by saving each year. That's the sum of annuity due formula we just did, where every year you put in more money. And then part B, she stops making more deposits. Whatever she had at the end of the sum of annuity due formula becomes her principal for a compound interest formula that goes on for 33 more years. So just like this one, it's a two-part formula, but part one uses our new sum of annuity due formula. And if that seems complicated, then just save it. We'll talk about it next time and do one of these. For your turn-in homework, is a similar kind of thing, that you have some mix and matches of when am I using compound, when am I using sum of annuity due. Number 9 is a scary one. If instead of paying $13,000 a year for childcare in Eugene, you just took 2 years of $13,000 and saved, would that pay for retirement or not? So these are getting a little confusing because you have 3 different formulas: simple, compound, and sum of annuity due. But that's okay. We'll figure it out together next week. Any last questions? No? Okay, so maybe I'll see you Friday at 3:30, or maybe have a good weekend, and thank you for being in class.
Have a good one.
Thanks, David.